Good morning, all. I welcome all to the course on Mechanics of Solids. And it is one of the foundation courses in the study of structural systems. This course provides the fundamental concepts of mechanics of deformable bodies and helps the students to develop their analytical and problem-solving skills. The course introduces the students to various internal effects induced in structural members as well as their deformation due to different types of loadings. After this course, the students will be able to determine stress, strain, and deformation of loaded structural elements. For civil engineering students, this course is of great importance because idea regarding the mechanics of solids is very much important for the coming courses, structural analysis, structural design, and for designing various structural components. And the prerequisite for this course is engineering mechanics that you have studied in your first year. And the course outcomes defined by KTU, there are 6 course defines. First one is recall the fundamental terms and theorems associated with machines of linear elastic deformable bodies. Second course outcome, to explain the behavior and response of various structural elements under various loading conditions. Third outcome, apply the principles of solid mechanics to calculate internal stress strain, stress resultants, strain energies in structural elements subjected to axial and transverse load and also bending and twisting moments. Fourth outcome, choose appropriate principles or formulas to find elastic constants of materials making use of information available. And the next one, perform stress transformation, identify principal plane stresses and maximum shear stress at a point in structural member. And the sixth outcome, analyze the given structural member to calculate safe load or proportion cross section to carry load safely. And the first outcome comes under Bloom's taxonomy level of memory, and second one is understanding, and third, fourth, fifth, and sixth outcomes are the applications of the information that you have studied earlier. And the assessment pattern is also defined by KT. It is given here. Then it includes continuous internal assessment for 50 marks and end semester examination for 100 marks. End semester examination is of 3-hour duration, and there are two parts for that. Part A, there are 10 questions, 2 questions from each module, and each question carries 3 marks. And part B, there will be 10 questions, 2 questions from each module, and you have to answer 1 question from each module. So there will be, you have to answer 5 questions from part B, and each question carries 14 marks. Total 70 marks for part B, and altogether 100 marks for the end semester examination. And a continuous evaluation pattern that includes attendance for 10 marks, continuous assessment that is 25 marks, that includes 2 tests of 50 marks, and quiz assignment or course project of 15 marks. Total 50 marks. And there are 5 modules, and the first module includes a review of statics, concept of stress, strain, etc., modulus of elasticity, stress strain, diagram of mild steel, factor of safety, working stress, axially loaded bars with uniform cross section as well as varying cross section, and statically indeterminate systems. Second module is regarding the temperature effects, then shear stress and shear strain, other elastic constants, modulus of rigidity, lateral strain, Poisson's ratio, volumetric strain, bulk modulus, and relation between the elastic constants. And here in the second module, you also need to study the strain energy concept and strain energy in bars carrying axial loads, instantaneous stress in bar due to gradual and suddenly applied load, then stresses in thin cylinders and spheres. And third module is regarding the bending moment and shear force. You have to draw the bending moment and shear force diagram for different types of loading for the different support conditions. And fourth module is regarding simple bending, and computation of bending stresses and the strain energy due to bending. All these comes under fourth module. And the last module is on stresses on inclined sections for uniaxial biaxial stress field, principal stress and principal planes, then strain along these principal directions, more circle for the determination of principal stresses, then columns, short and slender columns, Euler's and Rankine's formulas for the finding out the maximum load carrying capacity of short and slender. Now to the details of the course. You have studied engineering mechanics in your first year. In that we were dealing with the mechanics of rigid bodies. The mechanics consists of mechanics of rigid bodies as well as mechanics of deformable bodies. In mechanics of deformable body, that is itself consists of solid mechanics as well as fluid mechanics. Here the course is solid mechanics. And in itself there are elastic as well as viscoplastic materials are there. Here we are considering the behavior of elastic materials. That itself may be either linear elastic or non-linear elastic. We will deal with linear elastic materials in our course. Then the analysis may be either static analysis or maybe dynamic analysis. In the case of dynamic analysis, we need to consider the variation of the load as well as the response with respect to time. But in the static analysis, the loads as well as response variation with the time is not considered. We will deal with the static analysis of structures alone in mechanics of solids. We have to consider equilibrium as well as stability considerations. Mechanics of material is branch of mechanics that studies internal effects of stress and strain in a solid body that is subjected to external loading. Stress is associated with the strength of material from which the body is made, whereas strain is a measure of deformation of the body. You have come across the term stress and strain from your plus 2 classes itself, but we will deal with the stress and strain in detail in this course. Thorough understanding of the fundamentals of this subject is of vital importance because many of the formulas and rules for design cited in engineering codes are based upon the principles of this subject. There are various design codes for the design of civil engineering structures. IS 456 is code used for the design of reinforced concrete structures, and IS 800 that is used for the design of steel structures. You have to use these codes while designing steel as well as concrete structures in the coming semesters. For the understanding of the terms as well as the formulas, all these things, and for the proper usage of these codes, you should have a thorough understanding of mechanics of materials. Regarding stress, when we apply a force on a body, it will undergo deformation. There will be certain internal forces developed within the body against this deformation. That resisting force per unit area, it is termed as stress. We are applying a force on the body while the stress is induced within the body. And for the body to be in equilibrium, the external force should be equal and opposite to the applied force. And the magnitude of that stress is given by the resisting force divided by area. Since the body is in equilibrium, the magnitude of resisting force is equal to the applied force itself. That is a force by area. And the unit of stress, it is unit of force divided by unit of area. That is SI unit is Newton per meter square, also called Pascal. In structural design codes, that is in IS 456 and all other structural codes, you may come across megapascal because we usually represent the strength of permissible stresses of materials in megapascal. 1 megapascal is 1 Newton per mm square. Coming on to strain, when a force is applied on a body, it will have a tendency to deform. Due to this deformation, there will be change in dimension of the body. Strain, it is a measure of change in dimension of the body with respect to original dimension. That is, strain is defined as ratio of change in dimension of the body to the original dimension. Since both numerator and denominator are of same units, it's a dimensionless quantity. And the strain may be either tensile strain, compressive strain, volumetric strain, or shear strain. We can say one by one. Tensile strain. When a tensile force is acting on a body, the tendency is to elongate or increase the length of the body. Then increase in length of the body to original length of the body. The ratio of this one, increase in length of the body to original length of the body, is tensile strain, whereas compressive strain is the ratio of decrease in length of the body to original length of the body. This occurs when the force applied is of compressive nature. When we apply a pushing force to the body, it will have a tendency to decrease its length. The ratio of decrease in length to original length, that is what is compressive strain. You may come across the volumetric strain when there is a change in volume of the body. Due to the application of the force, if there is a change in volume of the body, the ratio of change in volume to original volume is a volumetric strain. And shear strain occurs when the shearing forces are there. We can see that in detail by explaining the shear stress. There are different types of stresses. Stresses are generally classified into normal stress and shear stress. Normal stress is further classified into tensile stress and compressive stress. Tensile stress occurs when the force acting on the body is tensile. Compressive stress occurs when the force is of compressive nature. And shearing stress is due to the shearing force, that is a force acting tangential to the surface. We can say one. Then normal stresses are tensile stress and a compressive stress. When we are applying a tensile force on a body, the tensile stresses are developed in it. Here we are considering a bar. It is subjected to two equal and opposite forces, that is the pulling forces at the two ends represented by P. Here we can consider a section along XX and consider the equilibrium of the body of this bar to the left side of it and right side of it separately. If we are considering the equilibrium of this part, external force P should be equal to the restoring force, and the stress, that is the restoring force per unit area, and tensile stress is equal to restoring force per cross-sectional area, that is, since it is in equilibrium, the restoring force is equal to the tensile load P itself, that is equal to P by A, and the stress is given by P by A. Then effect of this force, tensile force P on the bar, what will be the effect of that? Since we are applying a pulling force here, the bar will elongate. That is, the length of the member will get increased. And the tensile strain, that is equal to increase in length of the bar divided by original length of the bar. Coming on to the compressive stress. Compressive stresses occurs when the force is of compressive nature. Here, the bar is subject to the compressive force P. Due to the application of this compressive force P, there will be a reduction in length of the member. That is, the strain developed is of compressive nature and a corresponding stress is compressive. We can consider a section, and here the resisting forces are marked opposite to the direction of application of force, such that the part of the body is in equilibrium. And the stress developed, which is equal to the resisting force per unit area, it is compressive in nature. And a compressive stress is given by resisting force per unit area, that is again equivalent to the load applied by unit area or cross-sectional area, that is sigma is equal to P by A. Bearing stress is another type of normal stress, that is in fact a compressive stress. We can consider the case when one object is placed against the other. Consider the case of a building resting on soil. What kind of stress occurs on soil? The building resting on soil exerts a compressive force on the soil. That is, soil gets compressed because of the load acting on it. Such kind of stresses are termed as bearing stresses. And next is the shear stress. The stress induced in a body when subjected to two equal and opposite forces which are acting tangentially across the resisting section, as a result of which the body tends to shear off the section, is known as shearing stress. Here the things to be noted are the force is acting tangential to the resisting section, and the tendency of the body is to tear off the section. In this figure, the force P, that is acting tangential to the surface, and the joint, it has a tendency to tearing off. It will be more clear from the coming. To explain more about the shear stress and shear strain, here we can consider a rectangular box of length L and height h. Let the bottom of this box is fixed and let the thickness perpendicular this direction, let it be unity. Here we are considering the shear forces, shear stresses, and the shear force is acting tangential to the surface. The bottom surface is fixed, and at the top surface DC, a force tangential to the surface P is acting here. Here ABCD, that represent the initial shape of the body, and it's, as I mentioned, its bottom is fixed. And since the force P is applied at the top, this one A, B, C1, D1, the dotted lines, that represent the distorted shape of the body. That is, there is some angular distortion, and that is what is termed as shear strain. Shear strain is equal to transverse displacement divided by distance. Let us see from this figure, when phi is equal to very small, tan phi is equal to phi. And you know that tan theta is equal to opposite side by adjacent side, that is dd1 by ad. dd1, that is the dl, is the transverse displacement that divided by height. So phi, that is dl by h. It is an angular distortion and it is expressed in units of angle. Usually it is expressed in radian. That is regarding the shear strain. And coming back to shear stress, as in all cases, the stress is equal to the resisting force by area. Here in the section ABCD, let us consider a section exists here. Consider the portion of the body above that and the portion of the body below that separately. Each part that is in equilibrium. For this to be in equilibrium, applied force P, that should be equal to the resisting force R. That is, shearing resistance is equal to the applied force P, that divided by the shearing area. It is resisted by this area and its dimension perpendicular to that one is unity. So the shearing resistance, it is given by R by A, and the resisting force is equal to P, and the shearing area, that is equal to L into the dimension perpendicular to that one, that is unit thickness. So the shear stress is equal to P divided by L into 1, where P is the shearing force and L is the length of the surface tangential to which the force P is acting. Thank you all.